का बोतल है क्या एक खोलना? थैंक यू। सब ऑन है ना? अनिमेश जी सब ऑन है? Okay. So let us start. Good morning. So today we will discuss about recurrent neural network, RNNs, LSTMs, and transformers, and also large language models. Okay. So I think Sir was discussing about the basics of natural language processing. So I will be discussing the neural language models, because the RNNs, LSTMs, transformers, those are basically used for developing the language models. Transformers are the basic building blocks of this large language models. So I will try to discuss about these models, and if time permits, then I will also discuss about the different tokenization techniques. Okay, because tokenization techniques plays a very major role. Like how can we tokenize a particular sentence? Like how can we like tokenize, like given a particular sentence, how can we break the sentence into different words or the tokens? It's a very important task in natural language processing. There are different algorithms for tokenization. So if time permits, I will also discuss about that. So anyway, so let us start with the neural language models. And these slides are mostly taken from, there was a large language model course of IIT Delhi, and they have a very good set of slides. So these slides are mostly taken from those lectures. Okay. So you know that this language modeling is basically a probabilistic task. Like if you know the previous words, like I like pizza with lots of, if you know the previous words, now you have to basically generate the next word, and you have to predict, like there is a vocabulary. Okay, so you have a vocabulary of all the words. Like, and what is a vocabulary? Vocabulary is basically all the unique words in the corpus. So corpus is basically the training data. So you have a training data, and from the training data you can collect all the unique words, and that will be your vocabulary. Like in a dictionary, there are all unique words, and that is our vocabulary. So now in this corpus there are many sentences. Okay, so based on the co-occurrence, like whether two words are co-occurring or not, we need to calculate the probabilities. So like how many times pizza and the cheese, these two words are co-occurring. So based on this co-occurrence of the two words, we have to calculate their bigram or the trigram probabilities. And that way, basically, we have to see whether two words are highly co-occurring or three words are highly co-occurring or not. So these language models are based on this probability only. Like if you're in your training data, two words are highly co-occurring, then at the generation time also, it will try to basically associate these two words together. That is the idea. So like if I like pizza with lots of, now suppose you have many options. You can put here the cheese, you can put here the corn, you can put here the tree. Okay, so in your neural model, like there is a background language model, and this language model has calculated the probability of being cheese given this set of words, being corn given this set of words, given tree given this set of words, and how these probabilities are calculated from the training data. Okay, so in the training data there is a big corpus, and from the corpus only these probabilities are calculated. So if you change the corpus, there will be a change in the probability. Okay, accordingly maybe you will get different word here. So okay, so everything depends on your training data. So if you are changing your training data, accordingly there will be a change in the probability calculation. Accordingly you will be getting a different value here. Okay, so this is everything is basically the probability. So probability of associating cheese with this sentence, with the previous words. Okay, it's basically, you know, that it's a conditional probability. Like previously these words are being generated. Now what is the probability of associating the cheese with the previously generated words? So this is basically called the language modeling. Yeah, so basically it's a kind of a, you know, that conditional probability, okay, conditional probability or the joint probability. So you can also think of a language model as a system that assigns a probability to a piece of text, okay. So for example, if you have some text x1 up to xt, suppose you have t number of words, okay, then the probability of this text, so basically you want to generate t number of words. Suppose in a particular sentence, there are t number of words. You want to generate x1 up to xt. Okay. So basically, this is a probability problem, as I mentioned, and this is a conditional probability problem. First, you can generate any word. Okay. So it is p of x1. So you start generating the word which has the highest probability. Then it is a conditional probability p of x2 given x1. Then P of, P of x3 given x1, x2. Okay. This way, you have to calculate the conditional probabilities. Ultimately, P of x3 given P of x3 minus 1, x3 minus 2, x3 minus 3 up to x1. So this way, there will be a conditional probability. And so this is represented as multiplication of t equal to 1 to capital T, P of xt given x3 minus 1 up to x1. Okay, so this is basically and as I mentioned that these probabilities are nothing but the frequencies. Okay, so frequency of occurring two words in the corpus. These are the frequencies, and these frequencies we are calculating from the training data. Training data is called the corpus, and from the corpus we are calculating the frequency of occurring two words simultaneously. Okay, so training data is giving us the probabilities. So in general, you know that we can build a language model like this, that suppose you have a sentence, museums in Paris are amazing. Okay. And you have to like maybe you want to solve the named entity recognition task. You know what is the named entity recognition task? Named entity recognition means that you have to identify all the entities from a particular sentence. Entities means either the location names, organization names, person names, or miscellaneous. Like Ram is going to school. So Ram is a person name. Or here, museums in Paris are amazing. Paris is a location name. Or we are studying in IIT Patna. IIT Patna is a organization name. Okay. Or today is 27th of November. So this 27th of November is a date. So this comes under, miscellaneous. So this way, you know that there are various types of entities. And if you can identify the entities from a sentence, that is called the named entity identification. Okay, it's a very important task in natural language processing, identifying the entities from a given sentence. And it's a sequence labeling task. So basically, why it's called a sequence labeling task? Like based on the context, only you can find out whether it's an entity or not. Because you know that in English there is a clue. Like in general, entities are always start with the capital letters. No, like names are always starting with the capital letters. Organization names also start with the capital letters. Location names start with the capital letters. But in Hindi or in Indian languages, there is no clue. We do not have the concept of capital letters. So we in Hindi, you know that like Kavita. Kavita could be a poem, or Kavita could also be a name. Okay. मैंने ये पुस्तक कविता को दिया. Okay. तो ये कविता, whether कविता is a person name or कविता is a poem name, how to identify? This is called the word sense disambiguation. This is a very important task in NLP. How to disambiguate the meaning of a particular word. What is the exact meaning of a particular word? And this is a more difficult in case of Indian languages, because we do not have this capitalization. In English, it is very easy. they have the capital letter concept. So all the entities start with the capital letters. So it's a big feature. Whenever you see a capital letters, that means it is a starting of entity. But in Indian languages, we do not have the capital letter concept. So kavita is a ambiguous word. Similarly, in almost all the Indian languages, there are many ambiguities. Okay, so basically, that so based on the context only, you can identify what is the exact meaning of a particular word. In English, there are many words like bank, like I am going to bank. I am going to bank. So now bank could be river bank, or the bank could be a financial organization. So I am going to which bank? Am I going to, but if I say that I am going to bank to deposit some money, then meaning is very clear. And if I am saying that I am going to bank to with my dog to spend some time, so then that means it is a river bank. So this is called the word sense disambiguation, and you can simply understand the meaning of a sentence or meaning of a word based on the context. So yeah, so this is a very preliminary model of neural language model, where we can take the entire sentence, we can get a embedding, maybe binary, the 0-1 encoding, like like each word can be represented as a vector of having length v is the vocabulary length. Okay, and only in that particular position you can put 1 and all the other positions are 0. Okay, so if suppose in your vocabulary there are 10,000 words, so so museum is a word. In that position, you can put 1, all the other positions are 0. Okay, in that way, you can initially represent the word. And then there are some weight matrices, you multiply with them, then you pass through some hidden layers, you get some feature vectors, and finally, you get that for Paris, the corresponding class is the location. Okay, so this is we call the language modeling task. So we have the sequence of words, and we want the probability distribution of the next word. So that is our basically main task. Yeah, so but here the main thing is that main problem is the fixed window. So like when we are considering a particular word, we can only see a fixed context, like maybe left hand side few words, right hand side few words. Okay, but sometimes you have a long like some sentences are very long in English, like the shape who worked for a long time in Delhi now started a new business in Patna. Okay, here just imagine the shape and started a new business in Patna is separated by a long phrase. So in order to understand the appropriate meaning, you need to link the shape and who started the new business in Patna are same. So you do not need a fixed window length. You need a dynamic window length, or you need to see the entire sentence. Then only you will be able to understand the appropriate meaning. So that was the main problem here, that the window length was fixed. Okay, so yeah, so this was the idea that initially we have the one hot vectors, then we have the concatenated word embeddings, then we are passing through some hidden layers. Okay, and finally there was a so last layer is the softmax. Softmax gives us the what? Probability distribution. No, that probability distribution over the vocabulary, that which word is the most probable. Like given like the students open there, now what will be the next word? So we cannot predict the word. See, language models cannot generate the word. Over the vocabulary, it can only generate the probability distribution over all the words. Now you select the word which has the highest probability. See, neural language models cannot generate the word. What it can do, it can only generate the probability distribution over the words, over the vocabulary. And now you select that word which has the highest vocabulary. In machine translation also this is the thing. It is not generating the word. It will simply give you the probability distribution over all the words. And now you select the word which has the highest probability. So this is here also happening. So when the students open there, so books is having the highest probability. So it will automatically books will come here because books has the highest probability. So books will come here. Yeah. AI tool में जैसे AI tool में जो generate होता है word वो मैम कैसे अपने आप generate नहीं होता, वही तो मैं बोल रही हूँ कि बेसिकली हम लोग के पास vocabulary है. वोकेबुलरी हम लोग कॉर्पस से हम लोगों ने पहले एक प्री प्रोसेसिंग स्टेप होता है कि कॉर्पस से हम लोग जितना सारा वर्ड्स है यूनिक वर्ड्स से हम लोग एक्स्ट्रा कर लेते हैं. हम लोग के पास एक वोकेबुलरी बन जाता है, ठीक है ना. और ये क्या करता है ना, वो एक एक वर्ड का आउटपुट में कितना सारा नोट्स होगा, वोकेबुलरी में जितना सारा वर्ड्स है. अगर वोकेबुलरी में 10,000 वर्ड्स है तो आउटपुट में 10,000 नोट्स होगा, ठीक है. और सॉफ्टमैक्स तो डिस्ट्रीब्यूशन देता है, तो वो एक एक नोड में एक एक वैल्यू मिलेगा. 0.02, 0.001, 0.5 ऐसे ऐसे करके वैल्यू मिलेगा. और जिसके समेशन ओवर करके 1 ही मिलेगा, प्रोबेबिलिटी वैल्यू सम करके 1 मिलेगा, ठीक है ना. तो उनमें से तुम्हें मैप करना पड़ेगा, जिसका प्रोबेबिलिटी हाईएस्ट होगा उस कॉरेस्पॉन्डिंगली तुम्हें मैपिंग करना पड़ेगा कि वो नोड कौन सा वर्ड को रिप्रेजेंट कर रहा है. तो तब वो वाला वर्ड को तुम्हें वहां पर वो ऑटोमेटिकली करता है, वो मैप करके वो वर्ड को फेच करके वहां पर प्लेस कर देता है. जेनरेशन नहीं होता है, इसलिए तो प्रॉब्लम है अननोन वर्ड प्रॉब्लम, आउट ऑफ वोकेबुलरी प्रॉब्लम. अगर ट्रेनिंग डेटा में वो कोई वर्ड को नहीं देखेगा तो वर्ड वो जेनरेट नहीं कर पाएगा. अगर इसलिए तो हम लोग ट्रेनिंग में इतना एम्फेसिस क्यों करते हैं कि ट्रेनिंग डेटा में हम लोग ज्यादा से ज्यादा डेटा क्यों रखना चाहते हैं, क्योंकि अगर वो न्यूरल लैंग्वेजेस मॉडल्स अगर कोई पर्टिकुलर वर्ड सोचो कि ट्रेनिंग के टाइम पे वो देखा ही नहीं तो वर्ड वो जेनरेट ही नहीं कर पाएगा, क्योंकि उसका तो जेनरेशन कैपेबिलिटी है ही नहीं. वो तो सिर्फ वो वर्ड पिक कर रहा है. तो उसको बोलते हैं आउट ऑफ वोकेबुलरी प्रॉब्लम, अननोन वर्ड प्रॉब्लम. तो इसलिए तुम्हें ज्यादा हम लोग को फोकस करना है कि ट्रेनिंग डेटा डाइवर्सिफाइड हो. ट्रेनिंग डेटा में अगर मैक्सिमम यूनिक वर्ड्स रहेगा तब जाके इट कैन आल्सो जनरेट डिफरेंट टाइप्स ऑफ वर्ड्स. Yeah, so basically that yeah, so this was the you can study this paper, this Benjio et al. In 2003 they developed this in a neural probabilistic language model. Okay, so yeah, but here as I mentioned that the window length is fixed. Okay, but we need a neural architecture that can process any length input. Okay. Yeah, basically, so basically, fixed window is too small. Enlarging window enlarges W, and x1 next one multiplied by completely different weights in W. So basically, we need to have basically a recurrent connections. Basically, we can keep on unfolding the neural network as long as possible. Like if the sentence will be long, there will be recurrent connections. So we need a recurrent connections. So that was the idea. So that is the idea of recurrent neural network. So in the recurrent neural network, what happens is that we are having this input. So input sequence is any length, like there is no restrictions on the input sequence. X1, X2, X3, X4 are the words, maybe different input sequences. And these are the hidden states, okay? And apply the same weight W repeatedly. So on the input sequence, we are applying the same W repeatedly, okay? It's like a same unit we are applying on the different inputs. As if this is the same unit, there is a wrapping, and we are applying the same unit on the input repeatedly, okay? And then we are generating output, okay? And then this is serving as a context for the next unit, okay? So this is serving as a context for the next unit. So for the next unit, it is not only receiving the input, but also it is receiving the input from the previous unit. So, so that is the difference. that it is not only having a context, but it is also having the current input. So this way there is a recurrence. But this W is the same for all the inputs. So what is the thing? So basically, you know, xt are the one hot vectors, as I mentioned, that 0, 1 vectors. So the size is the size of the vocabulary, and in one place only you have to keep 1, or other places are 0. So if your vocabulary size is 10,000, so if the word da is appearing in the first place, then the first place will have 1, or other places will have zeros. Okay. Then this is the embedding. Okay, embedding we are putting here. There is a weight matrix. You are multiplying with a weight matrix. Then we are putting the hidden vector, hidden layers. Okay, so we are multiplying with the E, and then we are getting the embedding matrix. A0 is the initial hidden state. Then we are putting the sigmoid, and this is the thing WH into the previous hidden state plus the WE into the new input. ET is the new embedding. Embedding coming from the current word. Embedding coming from the current word is the ET. Okay, and B is the bias. So WH is the previous, the hidden state matrix, hidden matrix. And HT minus 1 is the hidden state. Plus WE is the this embedding matrix. And ET is the embedding, plus B is the bias, and this is the sigmoid. Okay, and this is the hidden state. And so this way we are generating the hidden states, and you know that finally there is a output distribution also. So y hat t equal to softmax u ht plus b2. So this hidden state is now passed through the softmax. Okay, this hidden state is now passed through the, there is a you know, see. So finally what happens is that there are so many layers, no? After so many layers, you are getting the final hidden vector, and this final hidden vector is passed through the U weight matrix and the bias, and you are getting the final distribution. Okay, so you have to decide the final word, no? So you are deciding the final word distribution over the words, the probability distribution over the words. So this is the output distribution. So this is the RNN based language models. So you know that you are passing through the hidden layers, and the final hidden layer, as if it contains the final, the overall representation of the entire sentence. So this overall representation of the entire sentence is passed through the softmax, and it is giving you the distribution over all the words.
How the initial hidden state is found, like the H0?
H0. So H0 you can initialize randomly, basically. Randomly you can initialize. You can initialize randomly. Yeah, so so the input sequence, so basically here there is no restrictions. No, you can keep on adding, because you know it's a recurrent network. You can keep on adding as much as possible. Like there is no restrictions on the input sequence length. So yeah, so advantages can process any length input. Computation for step T can in theory use information from many steps back. No, like as if basically it is carry forwarding, no? Like previous state, like as if this hidden state has all information of all the past states. So as if it is accumulating, like it is a kind of a summary of all the past states. Model size does not increase for longer input context. Some same weights applied on every time step, so there is symmetry in how inputs are processed. But disadvantage is that it's slow, because you have to keep on processing in a sequential manner. No, each word has to be processed in a sequential manner. There is no parallelism. Like in a sequential manner, you have to process the inputs. And in practice, difficult to access information from many steps back. Like we will see that was the point of having the attention mechanism. Like, you know, as like it's a sequential processing, maybe you will not be able to focus on some words. Equal importance you are giving on all the words. But if some words are more important, that is not, you are not able to put focus on. That was the problem with RNN. So now how to train the RNN network? So there is a concept called the backpropagation over time. So how to train an RNN network? So you have to get a big corpus of text, which is a sequence of word x1, x2, x3, and you have to compute the output distribution. This is basically yt, this one, okay, y dash over every step. So you have to compute the output distribution. So the RNN will give you output distribution, and you know the original. No, like if you have the original sentence, you know, like what is the last word, you know, and when you are passing through the RNN will predict some word. So RNN will predict some output distribution. And what is the actual distribution, you know. So now you have to calculate the this cross entropy. Okay. So like you know the original distribution, RNN will give you a distribution. So you have to calculate the cross entropy between these two distributions. Predict probability distribution every word given word so far. So the loss function on step t is the cross entropy between the predicted. This is the y hat. Okay, this is the y hat and the two next word yt. So basically, you know that yt is the correct word, and y hat is the predicted word. Okay, y hat is the predicted word and yt is the correct word. Like if there is a sentence that I love to eat pizza with dash. So suppose originally it is cheese and your model is predicting corn. So then there is a difference. So that difference loss you have to calculate. So y is the actual word and y dash is the predicted word. And you know what you know. They are the, suppose the one hot encoding. One hot encoding. One hot encoding means if the vocabulary size is 10,000, then for corn it is 1, rest are 0, or for cheese it is 1, rest are 0. Okay, it is a one hot encoding. So this is the cross entropy loss between the y and y dash. So you know this is the formula of the cross entropy loss, minus of w belonging to vocabulary. So all the w part of the vocabulary, ywt into log of y dash wt. Okay, so that means what? As I am taking the one hot encoding, so for rest of the rest of the places, like for y, all the places are 0. Only when the why, like only when the cheese is present, there only we are having 1. Okay, so basically that's why you have to only consider that place where y is 1. Rest of the places are 0 because this is a one hot encoding. So it becomes minus of, so in that place you have to see the value of the y dash vector, because y is a one hot vector. In the y vector, all the positions are 0 except cheese. Okay. Now for the cheese, what is the probability? Y hat is basically a probability distribution. So you have to see what is the value of the y hat in the cheese. So if it is a high value, then you are done. Then that means RNN is predicting correctly. But if it is a very low value, then that means there is a mismatch in the prediction. So that is the thing, that minus log of y dash x. This is the xt plus 1t. So basically you have to only consider that a particular value where cheese is there. So then you have to take the average. So average over the entire training set. And that is your overall loss. So now this loss you have to, so basically what you are doing, at each step you are calculating the loss. Okay. At each hidden state you are calculating the predicted probability distribution, and accordingly you are calculating the losses. And then negative log probability of open, negative log probability of JR, negative log probability of exams, and then you are taking the summation. So then there is also a concept called the teacher forcing. So teacher forcing means that though basically you maybe here you are predicting wrongly. Suppose here it is opened, okay, and next is there. So if you what you are expecting here in this y dash, there, but suppose it is not predicting there, but during the training time you will always fit there only. Okay, this is called the teacher forcing, that you will not enter y dash y hat dash here, but you will enter the correct input. This is called the teacher forcing. So one option is that whatever it is generating in the previous state, you give that as an input for the next state. Okay, that is the normal practice. But there is a concept called the teacher forcing, where we are always giving the correct input. Like if the correct input is there, we will give the correct input to the next state. So this is called a teacher forcing. So so this way we are calculating the overall error. And now this overall error, we have to do the apply the gradient descent. Okay. So we have to apply the stochastic gradient descent to calculate the gradient. So however, computing loss and gradients across entire corpus at once is too expensive. So we are calculating this overall loss. In practice, consider x1 up to xt as a sentence or a document. And now we have to apply the gradient descent allows us to compute loss and gradients for small chunk of data and update. So we have to apply the stochastic gradient descent on this error. Compute loss j theta for a sentence, actually batch of sentences. Compute gradients and update weights, repeat on a new batch of sentences. So we have to apply the gradient descent on this, and then accordingly we have to update all the parameters. So this is what we are doing. So suppose this is the situation that h theta. So we are doing like this. Okay. So you know that so this is the h0. Then this is we have backpropagation for RNNs. So we are propagating like this. Okay. WS0, then this is this is the forward propagation. Okay, how it is WH is the hidden weight or weight matrix of the hidden matrix, hidden layer. Okay, and now here we are calculating the error. Now this error has to be backpropagated. So what is the derivative of jt theta with respect to the repeated weight matrix WH? So we have to basically calculate the derivative of this j with respect to WH. Okay, so this is our task, that derivative of jt with respect to WH. Okay, and this is summation over I equal to 1 to t, derivative of jt with respect to WH. And we have to consider all the I, because this jt somehow it depends on all these tests, because that somehow the computation of this hidden state depends on all the previous states, no? So this chain rule. So by the chain rule, we have to compute the derivative of this j theta with respect to all the previous hidden states. The gradient with respect to repeated weight is the sum of the gradient with respect to each time it appears. Okay, so we have to basically we have to apply the chain rule of the gradient descent. So this is the multivariate chain rule, that you can see that given a multivariate function f of xy and two single variable functions xt and yt, here is what the multivariate chain rule says. So if suppose there is a function f which is a function of xt, yt, so when you are taking the derivative with respect to t, we are doing like this. Del of f by del of x into dx by dt plus del of f by del of y into dy by dt. No, this is a chain rule. So to take the partial derivatives, like df by dx into dx by dt plus df by dy into dy by dt. So to take the partial derivatives. So this is the derivative of composition function. So and then basically this is the thing that we have to back propagate like this. So we have to basically gradient sum at outward branches. So we have to basically back propagate like this. Like we have to take the gradient with respect to individual branches, and then we have to take the summation. So del f by del y equal to del f by del a into del a by del y plus del f by del b into del b by del y. Okay. So this way you have to take the apply the grid chain rule or the multivariate chain rule basically. So that is what we will be applying here. So what is this back propagation for RNNs? So yeah, so this is our main. So we are calculating the error here, and then this error has to be back propagated to all the hidden states. Okay, and WH is equal in all the hidden states that we have assumed. It in practice often truncated after 20 time steps for training efficiency. Okay. So this is the idea that we have to take the derivative of JT with respect to WH where I equal to 1 to T. So for all the time, for all the recurrent connections, we have to take the derivative. So this is like this. For here, it is the immediate, but for the others, you have to apply the multivariate chain rule. So backpropagate over time steps t equal to t to 0, summing gradients as you go. This algorithm is called backpropagation through time. So because there are t number of steps. So gradually we have to keep on updating the hidden states. Like first you have to update the first hidden states weights. Then we have to update the second hidden states weights. But all these are gradient descent only. You know that this W new equal to W old minus alpha into the gradient with respect to the error of the gradient with respect to that weight. So we have to apply the same formula for updating the weight matrices. Okay. So, but it will be over like in a sequential manner. Now it will be back propagation over time in a chain rule. So now but the problem, what will happen? So if your gradient will like you will keep on doing the gradients over time, like first with respect to this or hidden states, then with respect to these hidden states. So if suppose your gradients is a very small value, so what will happen? There is a problem called the vanishing gradient problem. So when you will reach the first few layers, you will not be able to see any effect of the gradient. Your gradient will vanish. Like you will get a very small value of the gradient. So if you will have a very small value of the gradient, then you know the gradient update rules. No. What is the update rule? The W new equal to W old minus learning rate into the gradient. So if your gradient is very small, then there will be no update at all. Everything depends on the update. No, update depends on the gradient only. So if your gradient value is very small, then there will be no update at all. So this is basically called the gradient vanishing gradient problem. So if your gradient is very small, then ultimately it will vanish. So when if your sequence is very large, you have many steps in between. So when it will reach the first few words, there will be no update at all. Those words will not see any updates at all. So this is called the vanishing gradient problem. Okay. So yeah, so there are some solutions for that vanishing gradient problem. And if your gradient is greater than 1, then it will keep, there is a vanishing exploding problem. So there will be too much updates. Okay, there will be too much updates. So both are not good. Okay. So yeah, so this algorithm, just remember, this is called the the backpropagation through time, because we are keep in a sequential manner, like how the way we train during the we process the sequence in a forward fashion, and now when we have trained, we process the error in a backward fashion, and this is called the backpropagation over time, through time. Now there are many uses of RNN. RNN before the transformation before the transformers were introduced, RNNs were heavily used in natural language processing research because it was having these recurrence connections. Okay, so like RNNs were used for name entity recognition problem because it can see the entire context. No, it was having the capacity to see the entire context. And I told you that in order to resolve the ambiguity, entire context, you need to see the entire context. That's why RNN was a very important. It was a very useful tool. Like the started cat knocked over the vase. Okay. So here the problem is called the part of speech tagging. So part of speech tagging is another important task in natural language processing. So here you have to identify the whether the word is a noun phrase or it is a verb phrase, it is an adjective, okay, it is a pronoun. So what is the part of speech of the word that you have to identify. For example, da is a determiner, started is a adjective, cat is a noun phrase, knocked is a verb, over is a in, da is determiner. So this way, bhas is a noun phrase. So you have to find out the part of speech tagging of the of each word. So again, the context plays a very major role. Depending on the previous words part of speech, you can easily determine the next word's part of speech. So it's again called the sequence labeling task. So here again, the this RNN was heavily used. Then for the name and recognition task, also the RNN was heavily used. Then there are many sentence labeling tasks where you do not have to give class level to individual words. So finally, for a given sentence, you have to give a class level. For example, sentiment classification or the emotion classification. Like what is the emotional state of the speaker or what is the sentiment of the speaker. Okay, whether the speaker is neutral or negative or positive, or whether the sentiment the speaker is sad or happy or disgust. So that you can easily understand from the given sentence. So it is called a sentence classification task. So like overall, I enjoyed the movie a lot. Okay. So given the entire sentence, you can detect the sentiment. So here from the final hidden state, you can predict a class level. Okay. It is a sentence classification task. So the final hidden vector is important. From the final hidden vector, you can predict a class level. So what are the problems with RNN? So as I mentioned that one problem is the vanishing gradient problem. So J theta you are calculating at the end, and then you are calculating the partial derivatives of J theta over time. Okay. So you know that this is the idea that J theta we are taking the partial derivative over time, and then we are updating all the weight matrices of all these all the layers. So yeah, like we are updating here, we are updating here, we are updating here. So vanishing gradient problem, when these are small, the gradient signal gets smaller and smaller as it backpropagates further. No, we are backpropagating further, so it will become smaller and smaller. So what will happen? The first few layers will not be able to see any update at all. So there will be no update at all. If the sequence is very long, the sentence is very long, there are many layers, it will not be able to see any effect. So why is vanishing gradient a problem? So like here you see one sentence. When she tried to print her tickets, she found that the printer was out of toner. She went to the stationery store to buy more toner. It was very overpriced. After installing the toner into the printer, she finally printed her. So here, what will be the output? Huh? Yes. So, but ticket is seen long back. Okay, ticket was in the first sentence. So just imagine in order to understand that this is a ticket, there is a long-term dependency. No, there is a long-term dependency. But you know that to learn from this training example, we have a this model, the dependency between tickets on the 7th step and the target what tickets at the end. It's a long term dependency. So, but we need to understand this kind of dependency. So we have to process the entire this 3-4 sentences together. Then only the language model can understand that here ticket is the appropriate word. Okay, but if you are there is a vanishing gradient problem, then you will not be able to update till you will come to the first sentence. But if the gradient is small, the model can't learn the dependency. This kind of long-term dependency, the model will not be able to understand if there is a vanishing gradient problem. Like you will be calculating the error at the end, but when you will update the first sentence, the gradient will be vanished. So there will be no effect of the error at all. So the model is unable to predict similar long distance dependencies at the test time. So how to fix the vanishing gradient problem? The main problem is that it's too difficult for the RNN to learn to preserve information over many steps. So basically the main thing is that we have to handle the long-term dependencies, and there are many such English sentences where we have to, these are many long English sentences where there are long-term dependencies. So in order to preserve this kind of long-term dependencies, we need to solve this vanishing gradient problem. So, so this is our hidden state, HT equal to sigma WH previous hidden state plus WX input plus bias. Okay. So can we preserve the hidden state in a memory? Okay. So instead of, simply coming from the previous hidden state, so can we keep like maybe entire hidden state, entire past is not important. No. Like for example, here in this particular sentence, she found that the printer was out of toner. She went to the stationery store to buy that toner. So it is such a complicated sentence. But for this sentence, after installing the toner into the printer, she finally printed her ticket. So for this sentence, maybe only the first sentence was important. In between sentences are not important. Okay. So what happens in our day-to-day life also, like our memory processes many information. No, but you know that our memory decides which is important, which is not important. And accordingly, we forget many incidents, but we do remember many past or very old incidents. No, like our memory decides which incident to be remembered and which incident to be forgotten. So accordingly, can we also trick, like no need to remember all the past sentences or all the past words. So or, according to the context or according to the task, it will be automatically decided which information is important, and accordingly the memory will decide that yes, this information is relevant, and this information will only be kept in the memory or in the hidden state. No need to keep entire information in the hidden state. So that is basically the idea. In the RNN, we are keeping a abstract representation of the entire past in the hidden state. Okay, there was no focus on the relevant information, on the non-relevant information. But if we are mimicking the human mind, in human mind is always filtering out the relevant information, and we are forgetting the irrelevant information. So similar concept if we can incorporate in the neural architecture as well. So that was the concept of LSTM, long short-term memory network. Okay, so that we let us forget the irrelevant information and let us only focus on the relevant information, and only in the hidden state we will be keeping the relevant information. Yeah, so how about an RNN with separate memory which is added to? This is called a long short-term memory. And then creating more direct and linear paths through connections in models. So there are other there are many solutions to solve this vanishing gradient problem. One is this long short-term memory. other are the attention. In through attention, we can put weightage to the past words. So if some words are more important, we can put more weightage to them. Okay. So then there is residual connections. So these are also some ways to to basically help in improving the gradient descent, this vanishing gradient problem. So what is the LSTM? So LSTM is also heavily used in neural in natural language processing, and before transformer only, people used to use the LSTMs, RNNs, GRUs, etc. But after the introduction of transformers, now the NLP research is mostly shifted towards the transformers, because transformers are pre-trained, already trained on a huge amount of data. So, people are not using that. So a type of RNN proposed by these two researchers in 1997 as a solution to the vanishing gradient problem. So on step T, there is a hidden state HT and a cell state CT. So these both are vectors of length n. The cell stores the long-term information. Okay. The LSTM can erase, write, and read information from the cell. So the cell is a kind of a memory. Cell state is a kind of a memory. The selection of which information is erased, written, or read is controlled by three corresponding gates. Gates are calculated things whose values are probabilities. Okay. So the gates are also vectors of length n. On each time step, each element of the gates can be open, closed, or somewhere in between. Okay, so gate can be open, closed, or somewhere in between. The gates are dynamic. Their value is computed based on the current context. So yeah, so gate will control. So whether you want to write information, we want to erase information. Okay, so we have seen in digital logic the gate, the part of why gates are important. So we can either open the gate or close the gate. So okay, so that is the gate. So yeah, so there are three gates in the long short-term memory. One is the forget gate. So forget gate will decide how much you want to forget. Okay. So like as I mentioned, our memory is forgetting some information or some incidents. Similarly, in neural network also, forget gate will decide how much of the cell state, like previous cell state, you want to forget for the next state. Okay. Input gate controls which parts of the new cell content are written to cell. So forget gate controls what is kept versus forgotten from previous cell state. Input gate controls which parts of the new cell content are written to cell. And output gate controls what parts of cell are output to hidden state. Okay, so these are the three gate. Forget gate controls what is kept versus forgotten from previous cell state. Input gate controls what parts of the new cell content are written to cell. And output gate controls what parts of cell are output to hidden state. Okay. And so these are the operations you can see. So the forget gate is the sigmoid. So we're using the sigmoid. All gate values are between 0 to 1. Probability distribution only. So WF into HT minus 1 plus UF into XT plus BF. The input gate WI into HT minus 1 plus UI into XT plus BI. And output gate WO into HT minus 1 plus UO into XT plus B0. So new cell content, this is the new content to be written to the cell. Okay. So this is a tannage of WC HT minus 1 plus UC XT plus BC. And cell state erase forgot some content from last cell state and write input some new cell content. So it is basically combination of forget into the last cell state plus input get into the this one cell state. Okay, it is a combination of these two. Forget gate into the last cell state plus input gate into the C dash T. And HT equal to OT into tan CT. hidden state, read out some content from the cell. So this way, you know that this is all these are vectors of some length n. So you know that this way, so we are there are three gates: forget gate, input gate, and the output gate. Okay, so we are controlling this. We are having these three gates, and they are basically using these three gates to create a content a cell state, and also then the new cell state. So C dash T is the in intermediate cell state, and using the C dash T and the old C T minus 1, we are generating the new cell state, and ST is the hidden state. So this is the basic building block of a LSTM. So you can see first, XT is passed through the sigmoid, and you know that this is the previous hidden state. So you know that this is the thing that this is the that we are passing like this. So this is basically that all these operations, whatever we have mentioned, are performed in this particular block. Okay, so this is a in block inside a block LSTM block, and all these operations are done inside this block. Okay, this is a unique unit block of LSTM. So how does LSTM solve the vanishing gradient problem? So LSTM architecture makes it much easier for an RNN to preserve information over many steps. So basically here what happens is that we have this forget gate, and forget gate is multiplied with the previous cell state. Okay, and it is able to forget some part of the previous cell state. Okay, forget gate is multiplied with the previous cell state, so it is helping us to forget a part of the previous cell state. So so for example, if the forget gate is set to 1 for a cell dimension, and the input gate set to 0, then the information that the cell is preserved indefinitely. If the forget gate is 1, then we are not forgetting anything. Okay. In contrast, it's hard for a vanilla RNN to learn a recurrent weight matrix WH that preserves information into the hidden state. In practice, you get about 100 time steps rather than 7. LSTM does not guarantee that there is no vanishing or exploding gradient, but it does provide an easier way for the model to learn long distance dependencies. So basically, because of the forget gate, it is forgetting a part of the previous inputs. Okay, so that basically helps here LSTMs to keep only the relevant input. So that is the idea. So there is no, but it does provide an easier way for the model to learn long-term dependencies, because it now knows where to focus on. It is not keeping the irrelevant information in the cell state. It is forgetting the relevant information through the forget gate. It is only keeping the relevant information in the cell state. Yeah, so this vanishing or the exploding gradient problem is not only a problem of the RNN. Okay, it is also problem of many other neural networks. Like if you want to make a dense neural network, like there are multiple layers of neural networks, then it is a problem of all the neural networks. Okay, so like not only it is a problem of the RNNs, but it is a problem of all the neural networks. Like if you are having multiple layers of multiple hidden layers of neural network, then the same problem will arise, because you have to backpropagate the error, and you have to keep on calculating the gradient with respect to multiple hidden layers, and these are chain rules you have to apply. Backpropagation over time only you have to calculate. Okay, so basically that this vanishing gradient the problem will arise in normal neural network as well. So there must be some other solutions also. So one solution is basically that add more direct connections. So the thing is that we can do like this, like suppose X is there, so we are having some weight based layer, but this is called the residual connections. No, that we are not only adding this fx, but also the original X. Okay, in order to have a direct effect, we're also adding the original input here. So X is also added, like activation function is F. So we have added the activation function F over X, but we have also added X. Okay, so the original X is also added. So lots of new deep feed forward or convolutional architectures add more direct connections. So it is called the residual connections, that you not only pass X to the activation function, but then you also add the original X with the after the activation function. So residual connections occur ResNet, also known as the skip connections. The identity connection preserves information by default. This makes deep networks much easier to train. Or we can also have this kind of dense connections called the dense net, directly connect each layer to all the future layers. Okay, so we can have more such connections, not only sequential connections. Like in RNN, we have seen the sequential connections, but we can also have this kind of dense connections. Like this layer is connected to all the other layers. Okay, so it's not only sequential connections, but there are also dense connections. So highway connections occur highway net, similar to residual connections, but the identity connection versus the transformation layer is controlled by dynamic gate, inspired by LSTMs, but applied to deep feed forward or convolutional network. Okay, so basically we are having dense connections.
Can you show the last
Yeah.
last slide, ResNet one?
Yeah, please. Yes. This one
Yes, ma'am.
here, or I should go before also.
No, ma'am, ResNet one. Can you explain it again? What's the difference between ResNet and DenseNet? Is it about the future connection that we do in DenseNet or something else
Okay,
also?
so this is basically called the residual connection. So residual connection means that what we used to do is that we are passing the X with the weight, we are applying the weight matrix on X, no, and then we are passing through some activation function. No, that is the normal idea of a deep neural network. No, and we are basically applying the neural, we are applying some weight layer on X, and then there is a activation function on the weighted X. That way we are applying, we are perturbing the X. But now after this F is the activation function, suppose. Okay, we are not only after application of the like this activation function, we are again adding the original X, and then we are passing through the next layer. So we are not ignoring the original X. So we are still adding the original X after in here as well. So like, so what happens is that in general, in the normal neural network, we ignore the X. Like X is passed through the X is passed through the weighted layers, and then the activation functions, then again the weight layers, then the activation functions that we are processing, and we are getting the different feature vectors from the X. But we forget about the original X. But in the residual connections, we do not forget the original X, though we are getting the this kind of activation, we are applying the activation function on X, but we also add the original X with the with this function of X.
Okay, ma'am. So, and in DenseNet, what we are just connecting the first layer with the future layers. We are not passing the value of X, no?
No, yeah, we are not passing the, so that is very similar to obviously passing the original X only. So these are all solutions of the gradient, vanishing gradient problem. Because the vanishing gradient problem, you understood now that we are not able to there will be no effect of the gradient in the last layer because we are losing the gradient. So in order to solve this issue, somehow what we are doing, we are connecting the like now there are more number of connections. Like it's not only the sequential connections, but also the first layer is connected with the last layers, all the other layers. Maybe second layer is also connected with all the other layers. So there are more number of connections in between. Is it making sense?
Yes, ma'am. Right. Thank you.
Yeah. Yeah, so now these are some of the solutions of the vanishing gradient problem, and they're now they that you have seen that LSTM is very heavy in a sense because there are three layers in the LSTMs. There are three gates in the LSTMs. So there is a forget gate, there is a input gate, and there is a output gate. So forget gate is helping us to forget, because forget gate we are multiplying with the previous cell state. So forget gate we are multiplying with the CT minus 1. So we are multiplying forget gate with CT minus 1, and then the input gate is multiplied with this intermediate cell state, new cell content. And how we are generating this new cell content? WC into hidden state plus UC into new input. Okay, so basically new cell state is a combination of the previous cell state plus the input into this cell content, new cell content. So there are three states gates in the LSTM: forget gate, input gate, and the output gate. So output gate is the final output from the hidden state. Okay, these are the three gates from the LSTM. So now LSTM is very heavy block. Okay, LSTM has a very heavy building block, and we really want to reduce the size of the or computations of the LSTMs. So in order to reduce the computations of the LSTM, there was another neural network which was introduced, which is called the GRU. Okay, gated recurrent neural network. So what was in gated recurrent neural network? There are only two gates: update gate and the reset gate. So you know that somehow within this update gate and the reset gate, all these three gates are somehow combined. The forget gate, input gate, and the output gate are combined. So these two gates are basically doing the same operations like forget gate, input gate, and the output gate. So this is proposed by Cho et al. In 2014 as a simpler alternative to the LSTM. And on each time step T, we have input XT and the hidden state HT, no cell state. So basically update gate controls what parts of hidden state are updated as versus preserved. So update gate controls what parts of the hidden state are updated versus preserved. So basically, again, it is very similar to our forget gate only. Like because forget gate was also controlling in the LSTM which parts of the hidden state we have to update or we have to preserve. So this update gate is doing the same task. And reset gate controls what parts of previous hidden state are used to compute the new content. Okay, reset gate controls what parts of the previous hidden state are used to compute the new content, reset gate. So you know that, so this is the thing that reset gate and the update gate, these are the two gates. How does this solve vanishing gradient? Like LSTM and GRU makes it easier to retain information long term by setting update gate to 0. Okay, so you know that if you are making the update gate equal to 0, so basically if you are setting update gate equal to 0, then it will retain information long term. Okay, then it will keep all the backward information. Okay, if you are keeping the update gate equal to 0, then it will keep all the previous information. So new hidden state content reset gate selects useful, like, okay, so now we are generating two states: HT hash dash, which is tan age, WH RT dot HT minus 1 plus UH XT plus BH, and HT equal to 1 minus UT HT minus 1 plus UT HT dash. So this is the new hidden state. reset gate selects, you know that we are multiplying with the UT here. So reset gate selects useful parts of the previous. So RT is here. So RT is controlling which part of the previous hidden state will be taken into account, plus the new input. XT is the new input, and reset gate is RT is the reset gate. So reset gate selects the useful parts of previous hidden state, use this and current input to compute the new hidden content. And hidden state update gate simultaneously controls what is kept from previous hidden state and what is updated to new hidden state content. So update gate simultaneously controls what is kept from the previous hidden state and what is updated to new hidden state content. So 1 minus UT into HT minus 1 plus UT into HT. So basically, you know that UT is basically the update gate. So this is controlling that which part you want to read from the previous hidden state and which part you want to read from the new hidden state. It is a combination of this previous hidden state plus the new hidden state. So UT is basically controlling. It is a weighted sum of both. So LSTM versus GRU, researchers have proposed many gated RNN variants, but LSTM and GRU are the most widely used. So the biggest difference is that GRU is quick to compute and has few parameters. There is no conclusive evidence that one consistently outperforms better than the other. LSTM is a good default choice, especially if your data has particularly long dependencies or if you have lots of training data. Rule of thumb, start with LSTM but switch to GRU if you want something more efficient. Okay, so always start with LSTM, but you can always switch to GRU if you need like smaller computation or like less computation, because GRU has less number of gates, so it is less time consuming and also has less number of parameters. Okay, so if you need a smaller model, then you can go for GRU, but otherwise rule of thumb is that you can start with LSTM. Now we can also have some bidirectional LSTM. Sometimes you also need to see the, the future words or the past word as well. Okay, so we can also have the bidirectional LSTMs. So in a forward direction also we can see the words, and the backward direction also we can see the words. So maybe we can have two hidden states. One hidden state is generated from the forward direction, and the hidden state is generated in the backward direction. So forward here RNN is RNN FW, which is the forward directional hidden state into the XT is the current input, and backward RNN, backward directional hidden state into XT. Generally, these two RNNs have separate weights. There are two hidden states. There are two RNNs having two weights, and then we can concatenate these two hidden states, forward hidden state and the backward hidden state, and then we can have the concatenated hidden states.
During training only, we will have both the directions.
But there are two different weight matrices.
Yeah, but during testing, we can't see the future words. No? Like, for example.
Yeah. No, yeah, but then we can't see the future words. Yes. So but during testing, we can't see the future words.
It will be only for training.
Yeah. Then we can also have the multi-layer RNNs. Okay, they're like the same. We can have multiple layers of this kind of RNN structures. RNNs are already deep on one dimension. They unroll over many time steps. We can also make them deep in another dimension by applying multiple RNNs. This is a multi-layer RNN. So like you can see that, sorry, here picture is not correct. Like this way you can have the multi-layer RNNs. Okay, one layer after another. And the final layer we can only use, like, it can interact with multiple layers. Okay, like lower layer. So now the input, like, each layer is also taking input from the lower layer, backward, like left connection, left from the left side, lower side. This way it has to process more number of inputs. And so this allows the network to compute more complex representations. the lower RNNs should compute lower level features and the higher RNNs should compute higher level features. Like more number of features you can extract. Like if you will be able to like see the input multiple times, you will be able to extract more number of features. This is also called the stacked RNNs. Like, you know, that this is one layer, this is another layer, this is the third layer. So, and then maybe finally for the third layer, you can get the final hidden representation. Yeah, so this RNN was heavily used in NLP research. So from 2013 to 2015, LSTM started achieving state-of-the-art results, and LSTMs were heavily used for solving many tasks like sentiment classification task, name entity recognition task, part of speech tagging task. Successful tasks including handwritten written recognition, speech recognition, machine translation, parsing, image captioning. In the language modeling task, LSTMs were heavily used. And LSTMs and GRUs were become many very dominant approaches. Like in most of the NLP papers, you can see researchers were using mostly LSTMs and the GRUs. But then in 2019 or 18, attention and the transformer, those models were introduced. Those concepts came into the market. And then pre-trained models were also. Pre-trained models means those are already trained on a huge amount of data. So transformers have become dominant for all tasks because now the transformers can put focus on a part of the input. So for example, in a machine translation conference competition, you know that in WMT 2014, there were 0 neural machine translation system. In 2016, the summary report contains RNN 44 times. Okay, so WMT is a very important conference in machine translation. Okay, so all the big teams participate in WMT. They used to submit their papers in WMT. So in 2014, there was no neural machine translation system. In 2016, recurrent neural network based papers, there are 44 papers on recurrent neural network. Like there is to be summary paper, no? That like the organizers used to write a summary paper. So in the summary paper, RNN term was used 44 times. You can imagine that how many papers were based on RNN. And those systems own also. Like RNN based papers, RNN based systems own the first prize. In 2019, RNN 7 times, transformers 105 times. You can imagine people stopped using the RNNs and people started using the transformers. So, you know that they understood that RNNs are no longer used and people started moving towards the transformers. Yeah. So this is the thing. So now let us take a break and then we will discuss about the transformers. But these are some initial days NLP, okay, when people were when they are working on, you know, LSTMs and RNNs. But you know, as a starting point, you should use LSTMs and the RNNs. You'll be able to understand the system. But yeah, but then with the introduction of this attention concept and with the introduction of the transformer, there was a great change, shift change, you know, transformation in the NLP research. Okay, we'll take a 10 minutes break now. ये क्यों ऐसे होता है? ये तो मुझे स्टॉप करना है. इसको कैसे शेयर करूं? ये कहाँ चला
शेयर
गया?
क्या हुआ है?
हाँ?
इंटायर स्क्रीन
हाँ,
क्या?
हाँ. ओके. ये साउंड साउंड जा रहा है ना? जी. Okay, so I will discuss about the transformers, but before that, let me just give me a introduction of the large language models. Okay, so what is large language models? So again, I am telling that these slides are taken from this IIT Delhi. There was a course on large language models, so slides are taken from there. So you know that as I mentioned that language models are mostly they are giving us the probability distribution over a sequence of tokens. I told you that it is not generating any particular word, rather it is giving us a distribution over a sequence of tokens, and then we have to select the particular word which is having the highest probability. So, like for example, we have a vocabulary like arrive, Delhi, have, is, monsoon, rains, the, and then the language model. Whenever you have to select a particular word, you have to see that which word is having the highest probability, and accordingly that word will be selected. Okay, that is the idea. That the monsoon rains have arrived, so you have to see whether what is the probability of generating this particular sentence. So for each sentence, you have to calculate the probability, and I told you that how to calculate the probability by the joint, the chain rule. You have to calculate the probability of a particular sentence. So monsoon, the, have, rains arrived. So this sentence is syntactically incorrect. So it is not following the grammatical structure. So it is having a lower probability. Okay. So following the syntax and the semantics, the language model will basically they will calculate the probabilities. So the language models are trained on a huge amount of corpus. So they have a very good understanding of English grammar and also the semantics of a particular language. So, for example, we are learning languages, no, in our schools, in our colleges. So that's why we know that we have studied the grammar of a particular language. We know the vocabulary of a particular language. So we have a very good understanding of a particular language. So that's why you know that we can easily understand whether a sentence is grammatically correct or incorrect, whether the semantically correct or incorrect. So language models are also trained like that. So and this is all about the probability, okay? And the probabilities are calculated from the corpus only. It's the frequency of occurrence of the words in the training corpus. From the training corpus only, it is calculating the probabilities. So you know that there are sequence of tokens x1, x2 up to xl, and x1, x2, xl are the vocabulary in V, and you have to calculate the probability, joint probability of these words, x1 up to xl. So P of x1 up to xl, this joint probability you have to calculate. And the joint probability is the basically this one. By chain of rule, we have to calculate the joint probability. P of x1 into P of x2 given x1, P of x3 given x1, x2 into P of xl given xl minus 1 up to x1. And then you can apply Markup assumptions. Markup assumption says that the probability of a given word can only depend on the past word. Okay, like you can apply some bigram assumption or trigram assumption. That probability of a given word can only depend on the past word or past two words or past three words. So you can fix a window, and the probability of a given word can only depend on past few words. So pi of I equal to 1 to L, P of xi given x of 1 is to I minus 1. So this is the thing that give your sentences the monsoon rains have. Now what will be the next word? So given if the vocabulary is arrive, Delhi, have, is, monsoon, rains, it will calculate the probability of each word given the remaining sentence. So probability of arrived given the monsoon rains have. Probability of Delhi given the monsoon rains have. Probability of have given the monsoon rains have. So you have to calculate the probability of individual word given the rest part of the sentence. Okay, and then you have to calculate you have to take the word which is having the maximum probability. Like here you can see that arrived is having the maximum probability, so maybe you can select the arrived word. For generation, next token is sample from the probability distribution. So xi is basically following this probability of xi given xi1 to I minus 1. So these are also called the auto-regressive language models. Auto-regressive language models calculate this distribution efficiently, that is using the deep neural network. So auto-regressive language models are calculating the probability distributions for all the words. So why the large language models are called large? They are called large because they have huge number of parameters. They have huge number of weight matrices, or huge number of parameters, and also their training data set size is large. Okay, and their vocabulary size is large. Their training corpus size is large, and you can see that Elmo is having how many parameters? 994000000. GPT-3 is having 110000000 number of parameters. And now we have this GPT-3 by OpenAI that is having 17500000000. These many number of parameters they have. And then DeepMind recently released the GoFar. So in December 2021, which is very old now also, you can see how many parameters this model is having. So we are introducing more number of layers in the neural models, and we are also training with more amount of data. So that's why these models are called large language models. So model sizes have increased by an order of 5000x over just the 4 years. So like you can see the corpus sizes. Elmo was having a very small, like not small, like 10 to the power 9, number of tokens sizes. Elmo large was having 10 to the power 10 number of tokens. And GPT-3 is having more than 10 to the power 12 number of tokens. So you can see how many words are there in the training data. That's why these models are called the large language models. So other recent models are by Palm, OPT, Bloom, Gemini Ultra, GPT-4, which is having 1.76 trillion tokens or words in the training corpus. So you know that, for example, for GPT-4, we do not know number of parameters also. They have not announced officially how many parameters they have. So LLMs and in AI landscape, so basically that artificial intelligence, those are introduced to develop some like human beings are naturally intelligent. We have natural intelligence, but we want to make a computer system artificially intelligence, and that is not possible without the data. So with the help of data, we want to extract information, and from the information, we want to make the machines artificially intelligent. So that was the idea that if the system can behave like human being, and systems can have the intelligence. I mean, machines can have the intelligence. Then it will be called the artificial intelligence. And machine learning is a component of artificial intelligence, where we are giving huge amount of input output pairs to the machine, and from this input output pair, the machine will automatically understand the algorithm. Like in many domains, it is very difficult to derive the algorithm, like how to the speaker recognition algorithm or the handwritten recognition algorithm. No, like face recognition. Like for me, like if you will ask me, like suppose in a class there are 100 students, and you will ask, like if for a teacher it is very easy to identify a particular student. Okay, so the teacher can easily identify a particular student from a batch of 100 students. But if you will ask me that what is the algorithm in my mind, how I am identifying particular student's face from these 100 students, I will not be able to write down the algorithm in a plain paper. Okay, algorithm is not, I will not be able to explain. So basically, better to give a huge amount of input output pairs to the computer. Like we can collect multiple faces of the same student from different cameras, and those faces we can give to the computer, and from these faces the machine can extract different features, like maybe the complex, the color of the face, then whether the what is the hairstyle of the person, what is the distance between two eyes, the eye color, the shape of the nose, eyebrow shape, all these features the machine will automatically extract. And based on these features, the machine can easily detect the face of a particular person from a pool of faces. So so there are many domain, or there are many application areas where it is very difficult to write the algorithm by the human being. So in those application areas, we can ask the machine to derive the algorithm. So our task is only to give the input output pairs, and the machine can automatically derive the algorithm. So this is basically called the machine learning. So that is the beauty of machine learning. You simply supply the input output pairs, and the machine will derive the algorithm. Now then, deep learning is another sub branch of machine learning, where we have multiple layers. Now it's a kind of a black box system. We don't know the features also. So machines are deriving the features by itself. Like in machine learning, initially we are deriving our features. We are giving the features to the machine, and based on the features, machine was taking a decision. Like for example, this eye color, the size of the eyebrow, or the color, or the shape of the eyebrow, okay, the hairstyle. These are the features of a person, and based on this feature, the face recognition was done. But now, if we are simply supplying the face, and the features are determined by the a network, by the neural network, by a convolutional neural network, and then only we are in the output, we can only see whether the person's name, then features are also hidden, or features are also black box. It is a black box kind of a system. So this is called the deep learning, that there are many hidden layers, and these hidden layers are extracting some features which are not known to the user, or the application programmer. Then large language models are some subfields under deep neural network. As I mentioned, that when you have huge amount of data, and you are mostly concerned about the generation of text, okay, you want to generate new text, or you want to write some essays, or you want to write a summary, or you want to solve a new task. There is a in context learning, because they have general common intelligence. They are trained on huge amount of data, so they have human like intelligence. Like we human being are already in the schools and colleges, we have learned English. So now if you will ask me to write a essay on a new topic, I can write 2-3 paragraphs. Like if you will give me simply, as I have some idea, if I have some idea on a new topic, I can simply write a 2-3 paragraphs on the new topic. Only I need to have some understanding of the topic. Maybe that topic was not taught to me in my school or colleges, but I can simply write because I have a general common intelligence. Similarly, these large language models are having general common intelligence because they are trained on a huge amount of data. So they have this general common intelligence and they are very good in context learning. So for a new task, if you give 2-3 examples, they can easily understand how to learn that new task. And Gen AI is basically the generative AI when we are trying to generate new content like new image or new text, new videos. So this is called the generative AI. So Gen AI involves the use of deep neural network to create new content such as text, images, various forms of media. So this is the overall AI landscape. And this is the somehow history of the evolution of the LLMs, large language models. How the NLP research has started in 1966. This Eliza was a kind of a chatbot. So Eliza was developed by IBM, okay, by basically the MIT researchers, and this Eliza was started having some human-like conversations. So Eliza was a chatbot, and Eliza was able to do a human-like chat. Like you can ask a question to Eliza, and Eliza was able to give you an answer.
Normal conversation type.
Yeah, normal conversation type. Then this STNLP, statistically trained neural natural language processing system, was developed by MIT in 1972. That time statistical NLP was very important. Statistical means that from the corpus you calculate the probability. I told you that probability you can calculate for given a word, given the context, what is the probability of a particular word, the co-occurrence. That always that like how many times a hot is associated with dog. These two words are also co-associated. Okay, so this co-occurrence of the probability distribution, probabilities you can calculate from the corpus, and based on the probability you can generate words. Probability distribution you can generate. Then LSTM was introduced in 1998. Long short-term memory network developed by these two researchers, as recurrent neural network was able to learn from data and generate text. Then then GPU cards were introduced in the market in 1998, and that was a revolution. So when the GPU was introduced, graphics processing unit, when the GPU came into the market, then it was a big revolution in NLP research because we are having long paragraphs, long text document, and we really need memory, the processing power. So GPU was introduced in around 2000 by NVIDIA. And then, before that, it was very difficult to process huge text. It takes days, months to process long text. But after in the introduction of this GPU, it was a huge boost to the NLP research. So GPU was introduced in around 2000. Then IBM proposed their first model. IBM releases the IBM Model 1, the first version of its statistical machine translation system in 2001 or 2003. Then Facebook AI Research, they released this FAIR. Facebook AI Research is created. So they created an AI research center. Facebook created an AI research. I focused on advancing the field of AI through cutting edge research. Facebook also understood that they should invest more on AI. Okay, so they created a Facebook AI research in around this time, between 2006 to 2013. Facebook created their AI research center. Then IBM Tangora is able to recognize 20,000 spoken words. So spoken language also becoming very important. Spoken language understanding. What people are saying. Because Alexa, after that, Alexa was introduced. So, what people are saying, that you have to understand spoken languages. Then Google releases the Google Brain project, a deep learning artificial intelligence research project in 2014. Google Brain was basically introduced. Then Google Tensor Processing Units, TPUs. Google Brains using Tensor Processing Units internally. So it was released in 2015 only. So Google Tensor Processing Units. And then, OpenAI, in between this, OpenAI was also founded in around 2015 only. OpenAI, which is now developing all these, our GPTs and etc. OpenAI was founded in December of 2015. OpenAI founded to pursue the development of generative AI. So, this OpenAI was founded in 2015. Okay. Chief understood that OpenAI was founded in 2015, and then this 2016, the Stanford University's NLP group releases the Stanford question answering dataset. So this Square dataset is very popularly used for question answering. It's one of the largest dataset for question answering. Square dataset. If you are working in the question answering, must use this dataset. Stanford Square dataset. Stanford University's NLP group releases the Stanford question answering dataset, a dataset for NLP research. And in 2017, there was the introduction of transformer models. Okay, so and then this after 2017, the transformers were introduced. So the transformer models are introduced through papers like Google Transformer, a novel neural network architecture for language understanding and attention is all you need. So you can see that this paper was very important in the NLP research. So by Bhasan Yetel in 2017. So this attention, that is all you need. So this paper was introduced in 2017, and then there was a big drastic change in the direction of NLP research. So this was the history, in the language models, or basically in the language models. So initially researchers were working in in the LSTM's RNNs, and then they started working in the field of transformers. Yeah, so you know that what are the most recent transformers that is being used by the researchers? So yeah, so basically you know that this is the paper by the Google, that attention is all you need. Okay, the Google design transformer, and you know that we all are using this concept nowadays, and without the transformers we cannot imagine our life, no, like whatever models we are developing we cannot imagine without transformers. Nowadays nobody is using LSTMs RNNs, though I taught you LSTMs RNNs, but that is just for our understanding, just for our foundations, but nobody is using LSTMs RNNs. So this is the this is the paper. Okay, and it seems all these researchers have now left Google. They were with Google that time when when they wrote this paper. Attention is all you need. But now all of them have left Google. Maybe they have started their own startup. Okay. Then this BERT, pretending of deep bidirectional transformer for language understanding. This is also by Google AI language, and this BERT is very another important transformer model. We are always using BERT for encoding purposes. So this was introduced in 2018. The beginning of the use of transformer as language representation models. So BERT achieved a SOTA on 11 NLP tasks. So in the paper, they have shown the performance of BERT on various NLP tasks. So on 11 tasks, they have shown results of BERT. Okay. So results of BERT was shown like question answering, summarization. So they have shown results on various tasks. And now we are also having several other versions of BERT like distill BERT, tiny BERT, mobile BERT. So several other versions of BERTs are also available. So then someone was also OpenAI also started pushing the frontiers. OpenAI improving the language understanding by generative pre-training. So OpenAI released this particular paper by all these researchers, and there was an Indian also, Karthik Narasimham. So they started working on the pre-training of the transformers part. Okay, so this is the GPT. So this is the GPT 2018. So they what they did, they basically started releasing the pretend versions of the model. They pretend the transformers on a huge corpus, and they started releasing the pretend versions of the models. Use of decoder only architecture. So they were not these are not encoder decoder architectures, only it is a decoder only architecture. The idea of generative pre-training over large corpus. So then you know that we have the language models are unsupervised multitask learners. Okay. So then there was this GPT-2 in 2019. So the language models are unsupervised multitask learners, again by the OpenAI only. So GPT-1 was having 107 million parameters, and GPT-2 is having 1.5 billion parameters. 13 time increase in number of parameters. Minimal changes, some layer normalizations added, modified weight initializations, increase in context weight. GPT-1 is having 512 tokens, GPT-2 is having 1024 tokens. Okay. So you can see the performance boost across tasks. Like you can see that the GPT-2's performance over different tasks, reading comprehension, translation, summarization, question answering. So for like these are the results of GPT-2, like human, these are the result baseline. You cannot beat the human performance. Human is the baseline, and then by different other models. For the summarization task, for the question answering task, for the translation, for the reading comprehension. This is the T5. Okay, again Google released their another model T5. exploring the limits of transfer learning with a unified text-to-text transformer.
Ma'am,
So,
excuse me, ma'am, sorry, just
yeah.
ma'am. In previous slide, all the parameters which you have shown, ma'am, that's for reading and comprehension, translation, and summarization, ma'am. So, both GPT-2 and GPT-3 were measured on which parameters? For example,
So parameters are varying. Like for example, question answering is the accuracy. Then summarization is the rules 1, 2, L scores. For the translation, it is the blue score. For reading comprehension, it is the F1 score. So depending on the task, you need to change your metric. Okay, for different tasks, there are different metrics.
okay.
Yeah, like for summarization, we have the gold standard summary and you have the generated summary. So you can do the string matching. So longest subsequence match. So accordingly, you can calculate the rules 1, rules 2 score or the rules L score. So yeah, for question answering, if it is a binary question or multiple choice question, then you can calculate the accuracy, whether your actual answer is retrieved correctly or not. So you can calculate the accuracy. For translation, there is a blue score, which is also a kind of string matching only. So yeah, so depending on the task, you need to use the proper metric.
Okay.
So yeah, this is by the Google T5, which was introduced in 2019. So you can see this is another transformer which is being used. So similar broader goal of converting all text-based language models into a text-to-text format. Okay. So all the tasks are now converted into text-to-text generation basically. Okay. And it is but a encoder-decoder architecture. It's not a decoder-only architecture. It's an encoder-decoder architecture. Pre-training strategy differs from GPT and strategy more similar to BERT because BERT was their model only. So they were extending BERT only for T5. So basically now Meta, why only Google and OpenAI will release the papers or will release the models. So Meta also came into picture. So because till now we have seen the models by OpenAI and the Google. Now Meta also came into the picture. So Meta released Robata. Okay. So Meta released Robata, a robustly optimized BART pre-training approach. Okay, so you can see with University of Washington, this Facebook AI Meta, they released this paper, Robata. So replication study of BART pre-training measured the impact of many key parameters, hyperparameters of training data size, and found that BART was significantly under-trained and can match or exceed the performance of every model published after it. Okay, so they have shown that BART was not was under-trained basically and can exceed the performance of many of the models which are released after it. Then XLM was also proposed by Meta, which was in 2019 only. Cross-lingual. So now cross-linguality became very important. Cross-lingual language model pre-training. So till now, all the models are mostly trained on English corpus. So now Meta started working on the cross-linguality. So this XLM is also a model by Meta. So proposed methods to learn cross-lingual language models, and they obtained SOTA on cross-lingual classification, unsupervised and supervised machine translation. Because machine translation is supposed to be the most difficult task in natural language processing. So if you are able to establish SOTA on machine translation, that means your model is able to perform, you will be able to perform all other tasks efficiently. Because machine translation is the one of the most difficult tasks in NLP. Now OpenAI continues to scale. They propose GPT-3 in 2020. Okay, language models are few shot learners. They have shown the in context learning. Okay, that if there is a pre-trained model, there is a huge pre-training on a huge number of data, then you can give a few short examples and it can learn the new task easily. You only have to give only few examples. So, but it is having 175 billion parameters. OpenAI stops open sourcing. Now, OpenAI also stops open sources. They understood that their business is going down. So GPT-1 and GPT-2 are open sourced. But now OGPT from GPT-3 onwards, they stop open sourcing. They told that we will not, you have to buy our keys. It's no longer open sourcing. Okay. Google starts scaling to more number of parameters, more data, more corpus. But it is late, obviously. OpenAI was fast, GPT-3. So they released Palm. Google released Palm in 2022. Scaling language modeling with pathways. 540 billion parameters. Okay. And you see how many researchers are there. So I don't know. Like there are many Indian researchers, Shivani Agarwal. There are some Indian. The first researcher is also Indian, na? Akanksha Chaudhary. So she is also Indian, lady researcher. So yeah, so there are some Indian researchers as well. Google follows OpenAI in stopping open sourcing. So they also stopped open sourcing. It's now the LLM race. Okay, they also stopped open sourcing now. So it will not be open source. So now there are so many LLMs. So Microsoft, Nvidia, so all companies are having their LLMs. Okay. So OpenAI have this, and they also started developing the code. So the LLMs which can generate codes. The codex, OpenAI has developed the codex. DeepMind, DeepMind is also developing their own LLMs. Google, Lambda. So many LLMs are now there. Meta but promotes open source. Meta thought that now Google and OpenAI stops open sourcing. Let us make all the models open source. So Meta developed this OPT in 2022. Open Pretend Transformer Language Models. Okay, by Meta AI. Say a suite of decoder-only pretend transformers ranging from 125 million to 175 billion parameters, and it is open source. Now, in November 30, 2022, we saw a big revolution. ChatGPT was introduced, and now we cannot think our life beyond ChatGPT. Like I at least cannot think my life beyond ChatGPT. Whenever I am typing my email, I am asking ChatGPT to rewrite. Whenever I am writing anything, I am simply, my instruction is to ChatGPT is rewrite. So it's such a useful tool. So yeah, so I think most of our lives, there is a big change in our life. So now English writing is so easy for us. No, and but it's very easy also. People can easily understand, no, that whether I am sending my email or it is a AI generated text, they can easily understand. So, but we are not making enough mistakes in writing emails. So yeah, so it's a now big change. November 30, 2022, ChatGPT was introduced. It's a big interface. Yeah. Then BRD was introduced by Google. Meta introduced this Llama, which is an open source model. So Meta continues developing any open source model. Like, Google and OpenAI stopped open source model, but somehow Meta wanted to release open source model. So Llama is open sourced. Then Claude, Anthropic, a startup founded in 2021 by ex-OpenAI researchers, they releases the Claude in March 2023. Then OpenAI releases the GPT-4 in March 2023. Then Mistral AI releases Mistral 7 billion model in September 2023. Then Grok XAI, which is another, I think, startup only. They releases XAI is a startup. No, XAI is the Twitter AI.
Yes, ma'am.
Twitter, yeah. So XAI they releases the Grok. Then we have this Google releases Gemini in December 2023. So we will see in the 2024 we have seen more advancements, like we have this Gemma 2, then GPT-4 mini, Llama 3, Llama 3 by Meta. So these are the most recent models that we have seen in 2024. Yeah, so these are some of the recent models of this basically obviously of this year. So and the large language models continue, and yeah, so this is just an introduction, but now we will discuss about the transformers. Okay. Yeah, any question from the online participants?
इसका जो मेटा ओपन एआई सोर्स है वो बंद करने के बाकी सबको बंद कर दिया ओपन एआई सोर्स क्या रीजन
पॉपुलर होना चाहता है, they want popularity citations, ज़्यादा से ज़्यादा लोग यूज करें.
Yeah, hi ma'am. So
Yeah.
you mentioned, this is Ravi here. So you mentioned about the codex, right? So like if we see the chat GPT or Copilot, that also like generates the code, right? Like if we want to
Yeah.
like convert something which is in SAS into PySpark, something that it does. So what is the basic difference they have done? Is it like the codex one is more specific to like code conversion only?
Yeah, I think those are trained on this kind of data more.
Okay.
Yeah,
So for
means
code
those are
generation,
mostly
codex is
trained.
much better,
Yeah.
is it?
Yeah. Like those are mostly trained on those kind of data. Like in the chat GPT also you can have some kind of data, like they maybe have some log data or error log and etc. But main focus is on language understanding. But in Codex, the main focus is on generation of the code.
Okay, yeah. And is it open source? Like, is it like free to use or like we have to pay? Like,
Free. Codex is free. Huh?
It's limited बस month पे है. After that we have no questions.
मतलब फ्री नहीं है.
ChatGPT जैसे
अच्छा, no, it is free.
okay.
Like
Okay, thank
ChatGPT
you.
only you can use a few instructions are free, but then you have to pay.
yes
Few instructions
No,
are
in
free.
ChatGPT there are two options. One is like we can use free, another is like paid.
No, free.
Right.
So few instructions are free, na?
No.
If you want to run in bulk, then it is not free. Like for
Yeah,
example,
in bulk.
yeah. If you want to run a cell script, then it is not free.
Okay. Thank you.
So in ChatGPT, how much instructions are free? How many instructions are free?
for file upload or
You need to go fill in.
this is I think 5 or 6 up till 5 or 6 documents it's free. After that for the 4O meaning part 4O and 4. Other than that GPT-3 is normally open source. It will give limits for the 4O and 4O. And even in the paid version also they have introduced it that up till some tokens it's the paid version. Some tokens it will give afterwards it will limit it.
So why this Meta? So, give me answer to Ravi's question. What is the answer? Like why Meta has made their models free, open source?
If everyone starts making everything close, then how is the research community gonna?
But they also have to earn money, na?
But
Because their main purpose is to earn money. Like how will you they? So then Meta, how Meta is earning money?
Meta
It's not that much good, like OpenAI, if you are training them, OpenAI.
But Llama is reasonably okay, na? Llama 3 is not reasonably okay.
Llama 3.2, the new one which has came, those are okay, but those are trained on a very large corpus, and those models which are there, those are very heavy models. So like no one can get it get the whole model on their system. If like Llama, even in Llama also you will see 405 billion, which is the highest model they have. They have made it paid. They haven't kept it open source. They have kept the lower models open source. They have kept some higher models in paid.
Hmm. Okay, let us start. Okay, we will be now discussing about the transformers. Okay. Okay, so transformers are the basic building blocks of these large language models. So we have seen the RNNs, okay? That RNNs, we have seen that RNNs can be multi-layered or a single layered, okay? And RNNs can be easily used for solving any classification task or sequence labeling task, machine translation, part of speech to word processing, or name linear recognition tasks. So RNN was mostly used for solving this kind of sequence labeling task. And we have seen that RNN, the main basic problem was this vanishing gradient problem. So you know that so basically you know that the main problem was this linear the distance. If you have a long-term dependency, if your sentence is very long and there is a long-term dependency, then you will not be able to capture the long-term dependency well. So you know that order of sequence length steps for distant word pairs to interact means hard to learn long distance dependencies. Linear order of words is baked in. We already know linear order is not the right way to think about the sentence. Okay. So basically that is why you know that what happens is that what we have to do is we have to put emphasis on few words. So what is the solution? That maybe all the words are not important. So we have to put different weightage to different words. So like you know when we are calculating the hidden state, what we are doing, we are simply giving equal importance to all the past words. But that should not be the right way of calculating the importance. So importance should vary from word to word. So few past words are more important than the other words. So we have to give different weightage to different words. Okay. So that is the idea that now very similar to, you know, convolutional neural network, there is a windowing concept. So given a particular word, we have to see a window of the past words. And in that window, there are many past words. And each word is having a weight. And this weight will vary. Okay. Weight will vary from in the range of 0 to 1. So the words which are having higher importance will have higher weight, and the words which are having lower importance will have lower weights. So, so that is the idea. So so basically this is the thing that now we will be we will be calculating the attention. So attention means that we will decide in order to, when the embedding of a particular word will be calculated, it will be putting focus on some past words, but each past word will have different weight. Okay, and this is called the attention vector. Okay, and the attention vectors will vary from the the weightage value will vary. So all words attend to all words in the previous layer. Most arrows are also omitted. So let me, so basically what we will be doing, So let me discuss about the self-attention. So we are calculating the, suppose we are having a T number of words, queries, Q1, Q2 up to Qt. Okay, and each word is of d-dimensional. Like we can have a one hot embedding, or we can have a random embedding. Okay, we can initialize with a random embedding, or we can have a one hot embedding. Okay, so we have this T number of words as the queries, we have T number of words as the keys, and we have the T number of words as the values. Okay, now in the self-attention, we are putting attention on the same sentence. So given a word, we have to put attention on other words in the same sentence. The sentence remains same. Now suppose there is a query word, and the keys will basically will be other words. Okay, so let us see this. The queries, keys and values are drawn from the same source. Source means the same sentence. For example, if the output of the previous layer is x1 up to xt, these are the different words, one vector per word, we could let vi equal to ki equal to qi equal to xi. So suppose all the value, key and query, we are initializing to a particular word only. So suppose if the word is the Ram is going to school. So suppose we are fixing to Ram. So initially value, key and query is fixed to Ram. That is, use the same vectors for all of them. The dot product self-attention operation is as follows. So we are computing the key query affinity. So we are seeing how much is the similarity between the query and the key. So query and the key are how much similar. So what is the similarity between the query and the key? Okay, query key similarity we are computing. That is giving us the EIJ. Then it is the softmax. We are taking the probability distribution of the softmax. Alpha ij is equal to exponential ej by summation over j dash exponential ej dash. Compute attention weights from affinities, softmax. And finally, compute outputs as weighted sum of values, alpha ij into vj. Okay, so basically what we are doing, we are fixing value, key and query as the current word. We are computing the similarity between the query and the key, then taking the softmax and then multiplying with the value vector. So this is the thing that for each word we have three matrices: query matrix, Q matrix and the value matrix, and we have the projections over three matrices, and then we calculate the attention. Okay, in the diagram at the right we have stacked self-attention blocks like we might stack at LSTM layers, and we are putting at we are calculating the different weights for each word. So now so basically, but what happens is that here, okay, we are deciding that all the previous past words are not important, or all the future words are not important. We have to give focus on few words. Okay, that we have decided. But the thing is that there is no position information. Like maybe that we are not in English, position also matters, na? Like Mary give a book to John, or John give a book to Mary. So here position matters. If you are changing the position of a particular word, the meaning of the sentence changes. So, but in this particular attention mechanism, we are not incorporating the position vector. So we need to incorporate the position information. So so basically that's why what they have done is that in the value vector, they have also added the position information. Okay, the position vector. So this is the value vector, and now they have also added the position information. So PI is the position information. So position information could be the absolute position information, like whether this is the first word, or this is the second word, this is the third word. Absolute position information we can add, Or maybe we can also have the sinusoidal position representations. So we can have the sinusoidal position information, and then the sinusoidal position information can also be added. So there are different ways of adding the position information. So learned absolute position representations let all PI be learnable parameters. Learn a matrix and let each PI be a column of that matrix. Flexibility, each position gets to be learned to fit the data. Definitely can't extrapolate to indices outside 1 to T. So the people are still researching on how to give a good position representation. So this is the thing that what we are doing is that we are giving the self attention, then we are giving the feed forward, we are adding a non-linearity, we are adding Leroux activation function, and then we are passing through the MLP layers. So you know that we are putting the self attention, then we are passing through the non-linear layer, and then we are getting the output vector. So note that there are no element-wise non-linearities in self attention. Stacking more self attention layers just re-averages the value vectors. So we are having the self attention, then we are putting the Leroux activation functions, and then we are having the output. So, so this is the thing that now the another important thing is that when at the decoder side, so in the encoder side we can have the we can put the attention on all the words, like we can see the future words and also we can see the past words. There is no problem. We can see the past and future because the entire sentence is available. Like when we are applying the machine translation, like Ram is going to school, and the corresponding translation will be Ram school ja raha hai. So in the source sentence, the entire source sentence is available to us. Ram is going to school, the entire sentence is available to us. But when we are generating the target sentence, we are generating word by word. So the entire sentence is not available to us. So we have to mask the future words. Okay, we cannot apply attention to the future word. So this is called the masking. Okay, so what happens is that when we'll be applying to the decoder side, we cannot see the future words. We can only apply attention to the past word, but we cannot apply the attention to the future words. So this is the idea that we can only see the past words, but we cannot see the future words. So mask out the future by artificially setting attention weights to 0. So we cannot access the future words, we can only see the past words. So you know that the basis, self attention is the basis of the method, and specify the sequence order. Since self attention is an unordered function of its inputs, non-linearities at the output of the self attention block, frequently implemented as a simple feed forward network. Okay, so basically one thing is the attention, that we are changing the weight values of each word depending on the similarity. If we are calculating the cosine similarity, basically that dot product operation. If the word is more similar to the current word, there will be more weightage. If the word is not similar to the current word, there will be less weightage. Then we are adding the position vector also. If suppose the position vector is position, you know, we can apply the position vector. Then we apply the passing the feed forward connections. So you know, we are applying the non-linearities and masking in order to parallelize operations while not looking at the future, keeps information about the future from leaking the to the past. So this is the, you know, let me introduce the transformer model in general. So this is the transformer model. There is an encoder and there is a decoder. So in the encoder, we are having the word embedding plus the positional representation. I told you, word plus the positional representations. Then there are multiple layers in the transformers. Okay. And finally, we will get a hidden representation, encoded vector, and that will be given to the transformer decoder. So the transformer decoder will receive a input from the transformer encoder. Then it will pass through various layers. And finally, there will be a prediction. So depending on the task, So transformer can solve almost all the NLP tasks. It can solve machine translation. It can solve the summarization task. It can solve any kind of classification task. So depending on the NLP task, it can be used in various purposes.
तो ट्रांसलेशन कैसे करता है, लाइक हिंदी करना है
तो ये पहले हम लोग यहाँ पर देंगे राम इज गोइंग टू स्कूल, तो ये पूरा एक हिडन रिप्रेजेंटेशन देगा। राम इज गोइंग टू स्कूल का एक ओवरऑल रिप्रेजेंटेशन वो यहाँ पर देगा, और फिर एक एक करके एक वर्ड जनरेट होगा।
रिप्रेजेंटेशन।
पहले राम जनरेट होगा, मतलब मैंने बोला ना प्रोबेबिलिटी डिस्ट्रीब्यूशन जनरेट होगा। तो पहले वो एक राम मतलब फर्स्ट वर्ड एक प्रोबेबिलिटी डिस्ट्रीब्यूशन जनरेट करेगा कि कौन सा वर्ड होना चाहिए। वोकैबुलरी में जितने सारे वर्ड है सबका प्रोबेबिलिटी डिस्ट्रीब्यूशन जनरेट करेगा कि फर्स्ट वर्ड कौन सा होना चाहिए। तो राम के कॉरस्पॉन्डिंग जो प्रोबेबिलिटी डिस्ट्रीब्यूशन होगा उसका प्रोबेबिलिटी सबसे ज़्यादा होगा, तो अकॉर्डिंगली राम जनरेट होगा। उसके बाद स्कूल उसको विद्यालय जा रहा है, तो विद्यालय का प्रोबेबिलिटी डिस्ट्रीब्यूशन ज़्यादा होगा। तो ऐसे ऐसे करके वो एक एक वर्ड के लिए प्रोबेबिलिटी डिस्ट्रीब्यूशन जनरेट करेगा।
अगर कोई कोड अगर पाइथन में उसको अगर बोल रहा है मशीन को कि उसको बोल रहा है को बोल रहा है कि उसको आप जावा में करके दीजिए, तो वो क्या करता है, मतलब कोड का कुछ सिनेरियो समझता है और फिर वो जावा में ट्रांसलेट करता है, या जो कोड है उसको स्टेप बाय स्टेप लाइन बाय लाइन वो ट्रांसलेट करता है, कैसे करता है?
ऐसे कर पाता है क्या जावा को पाइथन में कन्वर्ट कर पाता है?
हाँ मैम, इस टाइप का रिक्वायरमेंट आता है इंडस्ट्रीज में, बट उसमें लाइब्रेरीज रहेगी जावा में, अगर वैसा केस है तो रहेगा। लाइक ये जो मैंने ये देखा है, लाइक
अच्छा।
मतलब मशीन लर्निंग के केसेस में तो मैंने देखा है, केस में कंफर्म में नहीं।
एलएलएम कर पाएगा?
नॉट श्योर, आई थिंक
एलएलएम कर पाता है? मतलब अगर तुम एक जावा का प्रोग्राम लेके बोलोगे कि कन्वर्ट दिस प्रोग्राम इनटू पाइथन, इट विल डू दैट। अच्छा,
वो कितना करेक्ट होता है, अप्रोक्सीमेट करेक्ट होता है, 100% करेक्ट नहीं होता, मे बी देयर आर सम चेंजेस कर सकते हैं आप वहाँ पे। और वो लैब में भी हम लोग देखते हैं ना कि कहीं पे अगर कोड में दिक्कत आ रही है तो वहाँ पे जिमनी सजेस्ट करते रहता है यहाँ पे आप चेंज करिए, तो लाइक वो कहते हैं
देखो ये लार्ज लैंग्वेज मॉडल के पास तो बहुत सारा नॉलेज है ना, क्योंकि उन लोग का जो ट्रेनिंग हुआ है, ट्रेनिंग डेटा सेट में भी शायद बहुत सारा प्रोग्राम्स था, और उन लोगों ने शायद पाइथन का मैनुअल भी ट्रेनिंग डेटा सेट में रखा है। मतलब इन लोगों ने तो ट्रेनिंग डेटा सेट डिफरेंट सोर्सेस से कलेक्ट किया है ना, विकिपीडिया या सोचो कि न्यूज़पेपर्स, सोशल मीडिया, डिफरेंट जो कंपनीज एरर लॉग्स देता है ना, एरर लॉग कभी कभी आउट रख देता है वेब में, वो सब एरर लॉग। तो मैनुअल्स, प्रोग्रामिंग मैनुअल्स जो इंटरनेट में मिला, सब कुछ उन लोगों ने कलेक्ट किया, और वो डेटा
पूरा
सेट से
गिटहब भी उठा लेते होंगे शायद।
हाँ पूरा गिटहब भी उठा लेते हैं, वो सही बोला, पूरा गिटहब पेज जितने सारा सब कुछ उठा लेते हैं। तो गिटहब में तो डेटा कोड वगैरह रहता है, डेटा सेट वगैरह रहता है, तो इसलिए उसके पास थोड़ा बहुत नॉलेज है, लेकिन उतना स्पेशलाइज नॉलेज नहीं है। जो कोड एलएलएम जो है, कोड स्पेशलाइज जो एलएलएम है, वो उसमें इंस्ट्रक्शन ट्यूनिंग भी हुआ है कोड जनरेशन के लिए। मतलब एक्चुअली लार्ज लैंग्वेज मॉडल जनरेशन का 3 स्टेप होता है, एक है प्री ट्रेनिंग, फिर है कि इंस्ट्रक्शन ट्यूनिंग, और फिर है ये अलाइनमेंट। अलाइनमेंट मतलब हम लोग इंस्ट्रक्शन दे सकते हैं कि ये इस टाइप का आउटपुट डिजायरेबल है और इस टाइप का आउटपुट डिजायरेबल नहीं है। प्री ट्रेनिंग मतलब सिर्फ ट्रेनिंग करते गए कि ये देखो इसको मतलब डिफरेंट टाइप्स का इनपुट उसको देते गए हम लोग, कि उस प्री ट्रेनिंग मतलब डिफरेंट इनपुट कलेक्ट करते गए और उसको देते गए। ठीक है, जैसे हम लोग स्कूल में पढ़ते हैं कि डिफरेंट टेक्स्ट बुक पढ़ते रहते हैं, पोएम पढ़ते रहते हैं, उसका क्वेश्चन आंसरिंग सीखते रहते हैं, ऐसे प्री ट्रेनिंग किया। इंस्ट्रक्शन फाइन ट्यूनिंग मतलब क्वेश्चन और आंसर ऐसे हम लोग ने दिया कि अगर ये क्वेश्चन है तो इसका आंसर ये होना चाहिए, इंस्ट्रक्शन ट्यूनिंग भी किया। और थर्ड स्टेप है अलाइनमेंट, उसमें हम लोग उसको इंस्ट्रक्शन देंगे कि अगर तुमने ये आंसर जनरेट किया तो ये करेक्ट नहीं है, और ये अगर आंसर जनरेट किया कि मुझे कौन सा आंसर चाहिए, मुझे पोलाइट आंसर चाहिए, मुझे रूड आंसर नहीं चाहिए, मुझे ऑफेंसिव आंसर नहीं चाहिए, मुझे तुम किसी तरीके से तुम्हें सेफ्टी अलाइनमेंट चाहिए, जैसे कि अगर तुम हेल्थ केयर में काम कर रहे हो तो तुम कभी भी तुम मतलब नॉनसेंस बात नहीं बोल सकते। तुम ऐसे बात बोलो जिसके बारे में तुम्हें पूरा नॉलेज है, तुम हेलुसिनेट नहीं कर सकते। तो वो है, थर्ड है अलाइनमेंट, वो बहुत इंपॉर्टेंट है, जो ह्यूमन फीडबैक देता है कि ये वाला आउटपुट ह्यूमन रैंक कर देता है कि एलएलएम का पैरामीटर चेंज करते हुए डिफरेंट डिफरेंट आउटपुट जनरेट होता है, और एक ह्यूमन एनोटेटर रहता है, और ह्यूमन एनोटेटर उसको रैंक कर देता है कि 1 to 5 के बीच, और वो फीडबैक देके फिर से हम लोग उसको फाइन ट्यून करते हैं कि सिखाने के लिए कि ये आउटपुट सबसे अच्छा है और ये आउटपुट सबसे बुरा है, कि सो दैट नेक्स्ट टाइम वो फिर से जब जनरेट करेगा तब वो वाला जो वाला आउटपुट खराब है उसको जनरेट नहीं करेगा। तो ये जो 3 स्टेप्स है ना, तो ये 3 स्टेप में एलएलएम ट्रेन होता है, चैट जीपीटी और जीपीटी 3.5 ये सब ट्रेन करने के लिए 3 स्टेप हम लोग को फॉलो करना पड़ता है। तो ये जो लास्ट स्टेप है जिसको अलाइनमेंट बोलते हैं, वो बहुत इंपॉर्टेंट है। तो मोस्टली आजकल सब लोग जो काम कर रहे हैं वो अलाइनमेंट में काम कर रहे हैं, क्योंकि प्री ट्रेनिंग तो पॉसिबल नहीं है हम लोग के सिस्टम में, क्योंकि हम लोग के पास उतना रिसोर्सेज नहीं है। एकेडमिक सेटअप में हम लोग के पास उतना जीपीयू सर्वर्स या इतना डेटा सेट भी नहीं है कि हम लोग स्टोर करें, और इतना, हाँ मतलब इतना हम लोग के पास इतने सर्वर्स भी नहीं है और उतना डेटा सेट भी नहीं है कि हम लोग इतना ह्यूज अमाउंट ऑफ डेटा पे हम लोग प्री ट्रेनिंग करें। तो हम लोग 2 चीज़ कर सकते हैं, एक है कि इंस्ट्रक्शन ट्यूनिंग कर सकते हैं, और थर्ड हम लोग ये लास्ट वाला स्टेप जो है अलाइनमेंट, अलाइनमेंट कर सकते हैं हम लोग, कि हम लोग उसको बोल सकते हैं कि ये वाला इनपुट सही है, आउटपुट सही है, ये वाला आउटपुट सही नहीं है, ये वाला इनपुट आउटपुट ये वाला हम लोग उसको बोल सकते हैं। तो अलाइनमेंट में बहुत सारा काम हो रहा है। तो कोडिंग में क्या होता है ना, जो 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 एलएलएम कोड स्पेसिफिक है उन लोग का प्री ट्रेनिंग ही होता है कोड के ऊपर, और नॉर्मल एलएलएम में शायद कुछ कुछ डेटा सेट कोड के ऊपर था। तो मतलब जैसे बोला कि विकिपीडिया पेजेस भी था उसमें, कुछ कुछ गिटहब पेजेस भी था, लेकिन जो कोड स्पेसिफिक एलएलएम है उसमें ट्रेनिंग डेटा में मोस्टली कोड्स ही था, तो लोग सही तरीके से कोड जनरेट कर पाते हैं। इसलिए तुम अगर चैट जीपीटी को बोलोगे कोड जनरेशन में तो उसमें गलती भी होगा, हेलुसिनेशंस भी होगा, गलती भी होगा, लेकिन ये जो कोडेक्स वगैरह ये सब जो कोड स्पेसिफिक एलएलएम है उसको अगर बोलोगे कोड जनरेशन में, उसमें ज़्यादा गलती नहीं होगा।
गिटहब को पायलट में भी अभी मैं जिस क्लाइंट के लिए काम कर रहा हूँ, दे आर यूजिंग लॉट कोड जनरेशन वगैरह के लिए।
हाँ ना, तो मोस्टली कौन सा लैंग्वेज में दे आर जनरेटिंग कोड्स?
पाइथन में।
पाइथन में ना। हम्म।
हाँ,
क्योंकि आजकल तो गिटहब में मोस्टली जो सब कोड्स अवेलेबल है वो सब पाइथन में ही है, तो उन लोगों को जो डेटा सेट मिला वो सब पाइथन में मिला।
बट मुझे लगता है जावा में भी ये जनरेट कर देगा, क्योंकि जावा का भी काफी ज्यादा कोड है, मतलब वैसा कोई प्रॉब्लम नहीं होना चाहिए। मेनली
हाँ।
इवन की कोड भी जनरेट ये करती है एलएलएम्स, तो इश्यूज रहता ही है। ज्यादातर मैंने देखा है कि टेस्ट केसेस वगैरह जनरेट करने में ये हेल्पफुल काफी ज्यादा होता है। थोड़ा बहुत
हम्म।
एरर रहेगा। मैं एक क्लाइंट के लिए काम कर रहा था, दे आस्क मी टू यूज चैट जीपीटी डायरेक्टली कोड वगैरह जनरेट करने के लिए। 1 मंथ का
अच्छा।
डेडलाइन दिया था, बट फिर भी काफी एरर्स आए थे, और फिर वो प्रोजेक्ट 1 मंथ से 6 मंथ तक चला था। तो
ओके।
लाइक थिंग इज लाइक दिस प्लेटफॉर्म डजंट नो अबाउट द डेटा, लाइक स्पेशल कैरेक्टर आ रहा है या कुछ वैसा एम्बिगुअस चीज आ रहा है, तो दैट इट कांट हैंडल एक्चुअली।
हाँ। हाँ, वही प्रॉब्लम तो है। तो वो सब कोड स्पेसिफिक एलएलएम यूज कर सकते हो, वो सब किया था क्या?
नहीं, मैं कोडेक्स मैंने नहीं यूज किया था, मैं चैट जीपीटी यूज किया था।
ओरिजिनल और कुछ है क्या कोड स्पेसिफिक एलएलएम कोडेक्स के भी?
गिटहब को पायलट है, फिर मतलब वही।
जब
ट्रेनिंग हुआ है मेन कोड के लिए। जीपीटी का आपका जीपीटी 1 का
जीपीटी भी कोड जनरेट करता है, मतलब ऐसा बात नहीं है, लेकिन हाँ कोड स्पेसिफिक नहीं है। इवन फिर हालांकि मेरी मेरी कंपनी क्या कर रही है ना कि लामा का यूज करके दे आर ट्राइंग टू बिल्ड बेसिकली देयर ओन मॉडल, मतलब स्पेसिफिक डेटा सेट लेकर के फिर से मतलब ट्रेन कर रहे हैं। देयर इज अ टूल दे हैव डेवलप्ड कॉल्ड बायोनिक, सो वो जनरली नॉट कोड स्पेसिफिक बट बेसिकली चैट जीपीटी टाइप का वो वर्क करता है। बेसिकली उन्होंने क्या किया कि इंटीग्रेट किया है मल्टीपल चीजें से, लाइक इट कैन रीड योर एक्सेल फाइल एंड शेयर पॉइंट से इंटीग्रेशन है, ऐसा है। तो उस पे ज्यादातर ये लोग फोकस कर रहे हैं, जो कि R&D में जनरली जो लोग वर्क कर रहे हैं, नॉट द कंसल्टेंट्स, बट वे लोग उस पे ज्यादातर कर रहे हैं फोकस,
Okay.
इंटीग्रेशन पे ज्यादातर।
Mm-hmm. Amen. Okay. So, okay. So, what is there in the transformer encoder? So, you know that. So, basically, you know that we are giving the word embeddings and the position representations to the transformer encoder. Okay. And there are three matrices: key, query, and the value matrices. So, these matrices are helpful in generating the attention vectors. And also, there is a concept called the multi-headed attention. So what is the task of multi-headed attention? So basically, we can put focus on multiple words, not only maybe in order to generate the embedding of a particular word, multiple words are important. So multi-headed attention can help us in putting focus on multiple words. So attend to multiple places in a single layer. Tricks to help with training, residual connections, layer normalization, scaling the dot product. These tricks don't improve what the model is able to do. They help improve the training process. Both of these types of modeling improvements are very important. So what we are doing, we saw that self-attrition is when queries, keys, and values come from the same source. The transformer does this in a particular way. So suppose x1 up to xt are the input vectors to the transformer encoder, and then we are calculating the queries, keys, and values. Okay. So ki is the key matrix, projection of the xi on the key matrix. Qi is the projection of the xi on the Q matrix, and value Vi is the projection of the xi on the value matrix. ठीक है, T matrix है
मैम व्हाट इज ओके की क्वेरीज, ओके गॉट इट।
Yeah, key query and the value of the matrices, and xi is a particular word. So we are taking the projection of xi along the key matrix, projection of xi along the query matrix, projection of xi along the value matrix. Okay, we are and then accordingly we are getting the key vector, query vector, and the value vector. Okay, these matrices allow different aspects of the X vectors to be used or emphasized in each of the three roles. So this key query value are the matrices, and we are taking the projection of xi along the key matrix, query matrix, and the value matrix, and we are getting the key vector, query vector, and the value vector. Okay. Now we are what we are doing. So basically, you know, as you have multiple words, like there are key number of tokens. Okay, and each token is d-dimensional vector. So you have a matrix of T into D. Okay, it is a concatenated input vectors. So now we have xk. Xk is the R to the power T into D. Xq is the RT to the power T into D, and xb is the T into D. So then the output is softmax of xq into xk to the power transpose. So you are taking the dot product of this q vector and the query vector and the key vector. So you get the projection of x along the query matrix, projection of x along the key matrix. Okay, and then take the transpose. So a projection of x along the query matrix, that will give you the query vector. Projection of x along the key matrix, that will give you the key vector, and then you take the dot product. Dot product means the similarity. You are checking the similarity between these two vectors. And then you take the probability distribution. Softmax will give you the probability distribution. So you get the probability distribution, and then that probability distribution you multiply with the value vector. The probability distribution will multiply with the value vector. So first take the query key dot products in one matrix multiplication. So this is the query key multiplication, and then you take the softmax, and then finally work and multiply with the value vector. So next softmax and compute the weighted average with another matrix multiplication.
मैम सॉरी यहाँ वैल्यू वेक्टर ये क्या है लाइक ये सॉफ्टमैक्स फंक्शन अप्लाई होगा सो दिस विल बी लाइक आफ्टर द फर्स्ट बैच ट्रांसफॉर्मेशन देन सेकंड बैच में भी यही कैलकुलेशन रिपीट होगा क्या थोड़ा सा वैल्यू मैट्रिक्स एंड के बारे में थोड़ा सा समझिए
ना मतलब क्या होगा ना ये हम लोग क्या करेंगे ना ये देखो इसमें क्या कर रहे हैं ना हम लोग वर्ड को डिफर करेंगे मतलब एक अगर एक्साई अगर एक करंट वर्ड है तो की होगा अलग वर्ड मतलब अलग वर्ड के लिए की कैलकुलेट करेंगे यू गेटिंग मी मतलब करंट वर्ड का प्रोजेक्शन लेंगे क्यू मैट्रिक्स पे और एक्सजे इज सम अदर वर्ड उसका प्रोजेक्शन लेंगे के मैट्रिक्स पे
ओके
ठीक है ना उसके बाद हम लोग इसका डॉट प्रोडक्ट वाला हम लोग सिमिलरिटी चेक करेंगे एक्सआई और एक्सजे के बीच ये दोनों वर्ड कितना सिमिलर है और उसके बाद वैल्यू वेक्टर फिर से एक्सआई है वैल्यू वेक्टर फिर से एक्सआई है ये इसके बाद मतलब
जो हमारे पास वोकैबुलरी में जो वर्ड्स है उसके साथ हम सिमिलरिटी चेक कर रहे हैं
एक्सआई इज और करंट वर्ड तो एक्सआई के साथ बाकी सब वर्ड का सिमिलरिटी चेक करेंगे जो हम लोग का एक उसके बाद उसका हम लोग प्रोबेबिलिटी डिस्ट्रीब्यूशन लेंगे और उसके बाद फिर से हम लोग एक्सआई का ही वैल्यू प्रोजेक्शन लेके मल्टीप्लाई करेंगे तो हम लोग को एक अटेंशन स्कोर मिलेगा जो बेसिकली हम लोग का एक एक्सआई का एक नया एम्बेडिंग जनरेशन में हेल्प करेगा
ओके थैंक यू मैम
So for word I, self-attention looks where xi transpose qt xkj is high, but maybe we want to focus on different j for different reasons. Okay, so basically maybe we want to focus on different j for different reasons. That's why there is also a concept called multiple heads. Like we can have different query key and the value vectors. Okay, instead of having only one query key and value vectors, we can have different query key and value vectors. Okay, so that is also possible that we can have different query key and value vectors, and then we can we can have different query key and value vectors where of dimension d by age, where age is the number of attention heads and A ranges from 1 to age. Each attention head performs attention independently, and finally output is the softmax xql into ql kl transpose xt into xvl, where output L is this r to the power d by h, and then we can concatenate all the outputs. Each head gets to look at different things and construct value vectors differently. So this is the thing that multi-head attention, we are getting only one, multi-head attention, we are only getting only one attention, but in the multi-head attention, we are getting different attention. So we will define multiple attention heads through multiple Q, K, V matrices, and then we can concatenate. Then there is a layer residual connections, what I already mentioned, that here we are passing through non-linearity, and we are passing through a layer, and xi minus 1 is applied passing through a layer, but we are also adding the original xi minus 1. Okay, so xi equal to xi minus 1 plus we are applying the activation function on the xi minus 1. So it is activation function is applied on the xi minus 1 plus the original xi minus 1. This is the residual connection. So you know that residual connections are thought to make the loss landscape considerably smoother. You can see without no residual, there is no smoothing on the loss function, but with residual function, there is a very smoothing. Then there is a layer normalization also. Like we can normalize the weights. Okay, layer normalization is a trick to help model strain faster, cut down on uninformative variation in hidden vector values by normalizing to unit mean and standard deviation within each layer. So we can do like this. So each weight matrix is normalized like this: x minus mu by root over sigma plus epsilon. So you can normalize like this. Okay, each weight vector is normalized like this. Then we can also have a scale dot product. Like in general, this is our original, original attention. But now we are normalizing like this. So we are normalizing like this, d by h. Okay, we can have a scale dot product. So this was our original attention, where we have done the dot product between the value and the key vector. But now there is a normalized dot product. Yeah, so now this was the encoder part. Now in the decoder, so basically in the encoder part, we have the multi-head attention, residual connection, layer normalization, feed forward, then again the residual plus layer normalization. Now in the decoder side, we have the masking. I told you we cannot see the future words. So we have the masking. And now there is another important thing which is called the cross attention. So cross attention means because we have two inputs to the decoder. One is coming from the encoder and other is the what decoder has already generated. So decoder is also generating a part of the target sentence and it is also getting an input from the encoder. So it will put a cross attention. Okay. So what it is doing, here there are two inputs. One is the output from the encoder, which is denoted by H1 up to HT, and Z1 up to ZT is the generated output from the decoder side. Okay, it has two inputs. So initially in the encoder there was self attention, and now in the decoder there is a cross attention. So we will be calculating the key and the value from the encoder output. So encoder is giving a hidden representation. So we'll apply the projection of the key vector and the value vector on the hidden vector. Okay, k into Hi and the v into Hi. We're getting the key vector and the value vector. But the query vector we are getting by projecting on the query on the z. Z is the output which is generated by the decoder till now. So decoder has generated some output. So that is the projection QZI. So then we are applying the similar dot product. So query into HK. Now this is HK. H is the hidden representation from the encoder and Z is the output generated by the decoder. The dot product, then the softmax into again the hidden representation of the encoder. Yeah, and then this is the all about the transformer, the encoder and the decoder, mostly the similar, but in the decoder we have the cross attention and also the masking. We cannot see the future ones. And there are great results for the transformers, like they have shown that on the machine translation task, the transformers are doing great. On the English, French, English, German machine translation, it is outperforming all the existing results in the original paper. Yeah, also for the document generation, also they are performing great. Yeah, so I think I have to stop now. Sir. Okay, so then. Okay, then, huh? We'll meet in the second half. There will be a demo, and tomorrow we'll meet.